when we get feedback from the switch, limit switch, the second arc gonna turn on the second chamber to eject the satellite. And at 500 meters, the third arc gonna turn on the third pressure chamber to separate the body tube into two pieces to release the main parachute. And in the same time, we get data in our human machine interface. The data that we got is attitude for our recovery system, and we get temperature, pressure, and humidity for the weather station idea. And we get also latitude and longitude to get the position where our rocket falls. And this is the recovery and the avionic system for our Z Phoenix.
The following circuits represent what my friend said here. The thermometer and the barometers are work in coherency to determine the altitude of the As I was saying, the thermometer and the barometer work in coherency to determine the altitude of the rocket, while the GPS is what determines the location of the rockets under the recovery, when they are under the recovery. So the microcontroller here, which is Atmel, is what manages all the capture and the command line that ignites the ejection system both for the nose cone and the body tube. An XB module is what communicates between the rocket and the graphical user interface service.
Vas-y.
Is what the XB module right here is what communicates between the rocket and the graphical user interface at the ground station. The data are transformed between this XB to this XB. And for the payload, the ejected payload right here, which is a nano satellite with a dimension of 10 to 10, is powered using three triple junction solar cells. And these triple junction solar cells have a unique way of layering the junctions, which allow us to absorb the most and the optimum wavelength of the radiation of the solar. A special mechanism is developed called the origami. It's a traditional Japanese art. It's called the rigidly folded origami twist. The mechanism is the origami twist is the origami twist is determined is made to enhance the surface in relation to the volume. For example, this origami twist allows us for a small amount of volume to enhance the surface to about 4 times, and hence increasing the power of the solar cells. Another mechanism is set in place for the communication, which is this mechanism of the folding the antennas. So there are 4 antennas that the satellite communicates with. 2 ultra high frequency with a frequency of 433 megahertz, and 2 other very high frequency with a frequency of 173 megahertz. So it's the antennas are rolled up in small chamber to minimize the space occupation while launching the rocket. So there's a wire that holds these chambers in order to keep the antennas from setting free, from stretching out and reaching their original form. These wires are cut by a thermal knife. The thermal knife is just a conductor that uses Joule effect in order to heat up the denim wire. This
Le système de déploiement.
and this is how it works. This, yeah.
And to show you the idea of the arc is presented by a high voltage generator. The arc is gonna still feedback come, and when the feedback comes, the arc gonna turn off. Okay. Yes, to make it guaranteed.
It's a pyrotechnic type of ignition, which the ignition will turn on the powder or the gas used and create a gas burst that bursts open the nose cone or the body tube. And that's it. Thank you for listening.
Oui, l'éjection, ejection system.
Yeah, the ejection system. Because we try to understand that you are like just briefly passed through, and you mentioned that this one is for the first ejection, right?
Yes, this for white one.
Fourth one.
Yeah,
Okay.
for separation of the nose cone, and this one for ejecting the satellite.
Okay.
This one is for ejecting. Its place is gonna be here.
Okay.
And it's gonna separate the body tube into two pieces.
Okay.
And the main parachute is gonna be guaranteed by the wire that we put with the main parachute.
Yeah, but we have like a drag. What is a drag? It's controlled
Yes,
by
the
what?
drag is guaranteed when the opening of the nose cone.
Yeah. Okay.
So this is the
Yeah, I understand. This is like a parachute. But how is going to ignite? This one is ignited by what? Is it powder?
yeah.
Black powder.
Yeah, there is two solutions. Yeah, black powder or any fire gases. Yes. Yes.
No, it's the black powder.
It is black powder.
Is it experimentally
Tell us what is the system.
Yes.
Black powder?
It is black.
Yeah, we push two
Yes.
solutions for this. Black powder or any fire gas.
Why does you said or means is a backup or you don't choose the right solution?
Not choosing the right solutions problem, but both are good solutions.
Yeah, I understand. But what you choose, which one you choose for your
Gases, because we
the
have
gas?
arc, yeah.
Okay. Good. Okay. I have a question. Serge, again.
ما حتى في التليفون معليش الا جينا شوف التليفون
Yeah, exactly.
We talked about this instrument. And inside you have a barometer.
في العمود اللي طبقت
Takes
ضبط الماء درتي بلاصتها
pressure
نسي هضرة في السيارة
of outside or
نسي هضرة
مروان
البيستون شعلوا وحدة
هي روح جيب صفيك على اللي قال لك هيا روح
جيب روح جيب
Through radio frequency.
روح جيبها روح
جيبها روح جيبها صح
in a way to calculate the altitude. So you have to measure,
تشعلها
the pressure, static pressure of the outside. So what's the relation between inside, because this instrument is located inside.
How you measure the outside pressure?
Tu mesures la pression.
Just a solution. Usually what we have to do, we drill hole. Voilà. Usually the chamber that where you want to measure the pressure and to calculate the altitude, we drill 3 holes. Enough holes, the diameter of the holes is small enough or big enough. Just when you have
measure la
just
pression
have
ضغط.
barometric, there is no dynamic pressure. It's just a barometric. Usually we drill 3 holes for that chamber. That means your instrument is inside, but is measuring the outside.
Yes.
Okay.
Yes.
And to show you the idea of black powder, that we're gonna present it to you with a simple idea, just to show you the pressure that we're gonna have. Yeah.
It is not secure enough because people is around.
It's secure. There is no danger. Yeah.
Okay.
Yeah. Just black powder, simple. And like that, we're gonna have a great pressure. Yeah. For the ejection. Yes.
You are talking about solar panel, new deployment system.
Yeah.
But we just see the support. We want to cells on the system. Did you try it?
If you make room for the
Yusuf.
Okay, I understood.
you are already tested? Unfortunately, we haven't had the time to make exact. We just make a simple prototype that utilize the same technique, but not with the.
So what is the issue? You are near to release it.
The issue is that we want to make the solar panels consume as much light and as much, just far enough so it won't cover the other sources of the solar panel.
No, I understood that. Why you didn't put directly the solar panels on the system? Which issues you have?
We
For
just
releasing
want the deployment system was just the purpose of the deployment system was just to enhance the power of the satellite. If the satellite has enough energy with just these solar panels, there's no need for it. But if the component inside needs more energy,
I want to maybe explain exactly my question. Why you didn't put directly a solar panel on that system? What is your actual problem you have now? Why you just do the simulation of the structure of the panel? Why you didn't put yet the panels?
Je peux répondre? Je peux répondre?
Yes.
Bah parce qu'on ne dispose pas de prototype réel pour faire exactement les calculs. On a essayé d'acheter un panneau, on a essayé de scier, donc ça n'a pas marché. Et sur le marché algérien, on n'a pas trouvé de cellule adéquate pour le dimensionnement adéquat de cahier de charge, imposé par le cahier de charge. C'était justement ça le problème.
I thought maybe you have some problems to put solar panels on the system.
no, we don't have that problem.
So, thank you.
Merci beaucoup. Donc, vers 5, on va prendre une photo de famille. Maintenant, ce que je vous ai là, je vous recommande de descendre votre fusée. Vous allez descendre en bas. On essaie d'être aux escaliers sinon. Et vers 5h, 5h30, on va annoncer qu'on va passer au deuxième tour.
Ok,
D'accord?
ça marche.
J'ai fait avec toute musique. Donc à 15 minutes, je m'en suis suppléant ici qui me suis pas vu. Je lève ma main et je dis 5 minutes. Ça veut dire qu'il vous reste 5 minutes. À 19, je vous marque 1 minute. Et je vous tolère une autre minute. Ça veut dire à 20 minutes 30 secondes, je vous demande de faire la conclusion. Qu'est-ce que ça veut dire la conclusion? Vous partez à la dernière slide que vous parlez. C'est pas la conclusion pour ce que vous êtes en train de dire. D'accord? Donc 20 minutes plus 1 minute au maximum. J'espère que vous avez respecté. Je sais que vous voulez parler en anglais, donc je vous mets en garde parce que souvent c'est pas la langue pratique pour vous, surtout pour les Algériens. Donc gérez bien votre temps parce que si vous manquez, c'est pas notre faute, c'est la vôtre. D'accord? Bonne chance. On vous écoute.
Ladies and gentlemen, members of the church, we are proud to be among you here in this competition. As a start, I want to introduce to you. Our team members. We come from the University of Hasiba bin Bulia of Shlep. We are 20 students and 5 professors from our university who supervise this work. Desert Phoenix, why? Hope rises like a phoenix from the ashes of shattered dreams. Last year we took the 6th place, but this year we determined to be among the first winning teams and be better than last year. We came back harder, stronger, and louder. This project of ours is composed of rocket design, electronic parts, project and time management, marketing, finance, self-evaluation, sponsors yes, and conclusion. The exploitation of space has the potential to yield enormous profits. However, with present-day means of space launch, various expendable rockets, characterized by costs of thousands of dollars per kilograms to orbit, the expense of launching the many heavy payloads needed to support activities such as asteroid mining is prohibited. It is therefore desired to develop a new means of Space Launch 1 which is technologically feasible and economically attractive. Let's start with my colleague.
First of all, we will talk about the design. As you can see here, the main description of our rocket. And on the left, we have the simulation using open rocket. On the right, using SolidWorks. Standard stability. We have stability values varies between 1 and 3. Lift gradient varies between 10 to 30. Stability time lift gradient varies from 30 to 100. Rocket finance varies between 10 to 20. Collision arrow less than 100% to limit the oscillation during flight. The nose cone. The choice of the nose cone is dependent on the flight region, and since our rocket is in transonic region, we have 3 options, which are X-Power, Hard X-Power, Parabol, Von Karman, and LV Hack series. Therefore, we have chosen X-Power with a finish ratio of 3 DOT's optimum performance. Since we will be in transonic for only 3 seconds, we won't need to increase the finish ratio. Here are the different nose cones that were mentioned earlier. The Hard X-Power series nose cone is generated by rotating the equation curved above the x-axis. The fin. This is the design fin using SolidWorks. Now we will talk about the fin drag optimization. The number of fin. Using the NASA research, we found that the optimum number of fin is 3. If we use more than 3, we will increase the friction drag. If we use less than 3, there will be decrease in stability. Fin cross section. Thinner symmetrical fins result in lower CT in subsonic, transonic, and supersonic. And depending on other research, we have chosen the NACA airflow as shown in the diagram, which is 006. Sweep angle. 45 sweep angle give less CD comparing to larger angle in subsonic and transonic. In supersonic, it's better to use 70 degrees. And now we talk about fin attachment. Fin are fixed with two centenary rings using screws as shown in the picture below, and also with the body tube using fillet. The parachute. For a smooth and fast landing, two parachutes must be deployed. One from the track and in the apogee that will reach 20 meter landing speed, and the second will be open in 500 meter altitude to land with 4.5 meter landing speed. And we have also the payload parachute, which gives us 8.5 landing speed. For our parachute to maintain stability, it must have a hole in the middle, as shown in the pictures. This is our type of parachute. It's not like the others. It's called the Aegis compact parachute. It has better drag confusion. Here our test that happened yesterday. Rocket performance. To find our rocket performance, we use this diagram, which are vertical acceleration, vertical speed, and altitude varies to time. And from that, we will find three phases. The propulsive phase, which varies from 0 second to 1.3. In this phase, our rocket will reach its maximum speed, which is 333 meters per second, and also the maximum acceleration, which is 285 meters per second. And then we have the ballistic phase. In this phase, from 2 seconds to 23 seconds, our rocket will be subjected to his own weight and the drag force, and therefore he will be in deceleration moment. And then the last phase is the descent phase and the deployment of the parachute. In this phase, our rocket will deploy the drag parachute in the apogee and the main parachute in the 500 meter altitude. And now, this table resumes our respective calculations, which are rocket flexion, buckling critical strength, parachute port tension, fiberglass fusion temperature, flutter speed, and fin flexion. And now I give the word to my colleague.
For the electronics part, we have the avionic circuit and the payload. For the avionic circuit, it's constructed of the temperometer, a temperature sensor, and a barometer, which will determine the right altitude to trigger the electronic system. While a GPS module is set to track the landing location of the rocket. An XP module is added to transmit data to the ground station. Human-machine interface is made to show the rocket informations at real time, as well as saving them and laterally accessing them. An XP module is set to receive these informations. For the recovery system, the recovery system has two parts. The first part is the parachute mentioned earlier, and the second part is the ejection system. The ejection system is a pyrotechnic thrust generator, which is designed to produce a small short-term amount of thrust to burst open the container with its contents. It's used for both the ejection of the nose cone and its contents and separating the upper body tube to the downer body tube and ejecting the parachute that will eventually recover the rocket. The following diagram shows the algorithm used for the ignition system. The altimeter constantly checks for the altitude, and when it reaches 3 kilometers, the microcontroller will trigger the ignition system, bursting open the container. A presence sensor is held in place between the nose cone and the body tube in order to detect the presence of the nose cone and give feedback to the microcontroller for assurance. With the same method, the rocket parachute will be ejected by the disconnection of the upper body tube and the downer body tube. For the payload, the ejected payload at a distant altitude is supposedly a nano-satellite powered by solar energy-based electrical power system, feeding a 1.31 watts load of different electronic components. And so the energy produced must deliver 1.52 watts. As a result, two pieces of triple junction solar cells are chosen to produce 2.62 watts, which is sufficient for this system. An additional mechanism is added to enhance the power to volume ratio, which is called the origami. The adopted origami is called rigidly foldable twist. This simple twist is able to increase the surface up to 4 times the original surface, hence the increase in power. The following mechanism is the one that stretches or rather spreads the origami fold. It is a 5-stick formation that is related to one another using pivots. There are also connected spring coils inside the stick. The first figure on the left is represents the way this mechanism is held to the satellite using a burning wire, and the second figure represents the spread mechanism. There is another mechanism, the deployment mechanism, which is the mechanism to deploy the antennas for the communication system. There are 4 main antennas in this nano-satellite prototype. The first 2 are ultra-high frequency, the frequency of 433 megahertz. Their length is 173 millimeters. The 2 other are very high frequency with a frequency of 145 megahertz with a length of 517. The mechanism works by rolling up the antennas into small chambers held by simple wire.